My talk today is concerned with packing effects in mixture separations. Such effects are also called entropy effects, and they manifest at conditions close to pore saturation. In this slide, I examine the fractional pore occupancy for a variety of mixture separations. Let's begin with CO2 hydrogen mixtures. Even if we operate at pressures ranging to 1 megapascals, the pore occupancy in the MOF copper TD PAT is less than about 0.3. For CO2 methane mixtures in nickel MOF 74, the fractional occupancies are about 0.6. And for CO2 nitrogen separations using, say, magnesium MOF 74, the operations are typically at conditions corresponding to an occupancy of 0.4. For nitrogen oxygen separations with LIX zeolite, we have pore occupancy of about 0.5. The same is true for krypton xenon separations with copper BTC. For ethane separations, the pore occupancies may increase to 0.7 if you operate at say 1 megapascals. These are separations of hexane isomers where at conditions normally used in industry, the pore occupancies are about 0.9. For water ethanol mixture separations, the operating under ambient conditions, we could have pore occupancies close to saturation. For xylene separations using a barium X zeolite, for conditions used in industry, the bulk fluid phase is in the liquid phase and the pores are completely saturation. The important message to be drawn here is that for heavier hydrocarbons and for aqueous mixtures of water and alcohols, and for xylene separations, we have pore occupancies higher than about 0.8, and this is the focus of my presentation. The takeaways from this presentation are summarized in the slide. Entropic separations manifest near pore saturation. Entropic separations rely on differences in saturation capacities and packing efficiencies. The saturation capacities depend on molecular configurations, molecular footprints, molecular sizes, etc. It's important to note that the entropy effects are anticipated by the ideal adsorbed solution theory. And one important characteristic of entropic separations is that we have near total exclusion of entropically challenged component at pore saturation. And in this presentation, we have used the simple Boltzmann expression, S is equal to KLN W, in order to explain and elucidate entropy effects using a checkerboard analog of adsorption sites within the pore topology. We begin our discussions by considering the separation of hexane isomers, normal hexane, NC6, and 2-methylpentane using MFI zeolite. MFI stands for mobile 5, consists of a set of intersecting channels. This is one unit cell, and one unit cell has 4 intersection sites shown here. So these are the intersection points. These are the zigzag channels. These are the straight channels, and the channel dimensions are 5.5 angstrom. These are the unary isotherms, where we see that the component loadings of both normal hexane and 2-methylpentane are identical in the Henry regime, but the saturation capacities are different. Normal hexane has a saturation capacity of 8 molecules per unit cell, whereas the saturation capacity of 2-methylpentane is restricted to about 4 molecules per unit cell. And the reasons are shown by the computational snapshots here, where normal hexane, the linear isomer, can locate anywhere along the straight channels or along the zigzag channels. However, 2-methylpentane, due to configuration and consideration, requires more legroom and prefers to locate at the intersection sites. And there are only 4 intersection sites per unit cell, and therefore the saturation capacity at say a pressure of 10 to the 4 pascals is about 4 molecules per unit cell. Only if you go to a very high pressure, say 1 megapascal, you can manage to locate 2-methylpentane within the channels. In a paper published in 1999, we had published data obtained from configurational bias Monte Carlo simulations for mixture adsorption of normal hexane and 2-methylpentane in MFI zeolite. The data are presented here. The component loadings are plotted against the total bulk gas phase fugacity in pascals. We note that when the total fugacity in the gas phase is less than about 1 pascal, the component loadings of both isomers are practically equal to one another. But as the total gas phase fugacity increases beyond a value of 2 pascals, the component loading of 2-methylpentane decreases to virtually 0, and the component loading of normal hexane increases to a total loading of 8 molecules per unit cell that corresponds to the saturation capacity of normal hexane. It is important to note that the ratio of the component loadings of NC6 and 2MP are not 8 to 4, i.e. in the ratio of the saturation capacities of the isomers, but as the total pressure is increased, the component loading of 2-methylpentane is progressively decreased. And we have near total exclusion of the entropically challenged 2-methylpentane, because these molecules, the branch isomers, can only locate at the channel intersections, whereas the normal hexane molecules can locate along the straight channels or along the zigzag channels. This is the view from the top, and this is the view from the side. This is a characteristic of entropically driven separation, that as the pores get increasingly occupied, the entropically challenged component is virtually excluded from the pore space. Another way to plot this data is to plot the mole fraction of the normal hexane as a function of the pore occupancy. The red circles are the configurational bias Monte Carlo simulations, and the dashed line corresponds to a mole fraction of 0.5. Remember that the mole fraction of the bulk gas mixture is maintained at 0.5 because the partial fugacities are maintained equal to one another in the bulk gas mixture, and therefore value of the mole fraction in the adsorbed phase larger than 0.5 as observed beyond a pore occupancy, say, of 0.5, this region we have a selectivity towards normal hexane, And we note that as the pore occupancy approaches unity, the mole fraction of normal hexane in the adsorbed phase approaches a value of 1. In other words, 2-methylpentane is virtually excluded from the pores at a pore occupancy of 0.1. This is going to be a recurring theme in all the separations we're going to discuss in this presentation. Entropic effects are in play at high occupancies, and the entropically challenged component gets increasingly excluded from the pore space. Let us seek experimental verification of the data that was first published in 1999 using molecular simulations. Let's look at first uptake experiment. Here I show experimental data on the transient uptake of mixtures of normal hexane and 2-methylpentane in MFI zeolite. The transient uptake experiments were conducted using infrared microscopy. The experimental data were published in this paper. This is a collaborative work with Professor Carrier, the University of Leipzig in Germany. And let me explain the experimental data. The details are available in the paper. Coffin-shaped crystals of MFI were exposed to a gas phase mixture containing equal amounts of the two guests, normal hexane and 2-methylpentane. And I show here 4 runs which were conducted consecutively. In run 1, the MFI crystals were exposed to a gas mixture at a total pressure of 2.6 pascals at a temperature of 298. The uptake of normal hexane is shown by the red line, and the uptake of 2-methylpentane is shown by the green line. After the crystals have equilibrated, the bulk gas phase pressure surrounding the particle of the crystals is increased from the equilibrated value at 2.6 pascals to 4 pascals. And then the uptakes of normal hexane and 2-methylpentane were monitored using IRM, and the results are shown in this portion of the graph. After it has equilibrated to a pressure of 4 pascals, the pressure was increased from 4 pascals to 12.2 pascals. And then we see the normal hexane loading within the crystals increases further. The y-axis shows the loading in the units of molecules per unit cell. However, we note that the loading inside the crystals of MFI zeolite for 2-methylpentane decreases as the pressure is increased from 4 pascals to 12.2 pascals. And this decrease benefits the uptake of normal hexane. And in the 4th run, the pressure surrounding the crystals is increased from 12.2 pascals to 102 pascals. And then we see that the component loading for normal hexane reaches a value that exceeds about 7 molecules per unit cell. Recall that the saturation capacity is 8. So, and the component loading of 2-methylpentane decreases to virtually 0. I present here below configurational bias Monte Carlo simulations of the component loadings for the mixture of normal hexane and 2-methyl pentane at precisely the same temperature, maintaining partial fugacities in the gas phase equal to one another, just like in the uptake experiments. These pressures, 2.6 pascals at the end of the equilibration step here, 4 pascal at the end of the equilibration step here, 12.2 pascals and 102 pascals are indicated by these vertical dashed lines. And if we examine these two loadings at these pressures of 2.6, 4, 12.2 and 102, we note that these uptake loadings correspond very nicely with the component loadings determined from configurational bias Monte Carlo simulations, which show clearly entropic exclusion of 2-methyl pentane from the pores of MFI zeolite. So the uptake experiments provide direct experimental proof of entropic exclusion. Entropy effects also play an important role for permeation of mixtures of normal hexane and 2,2-dimethyl-butane across an MFI membrane. Here I show experimental data for the component permeances of NC6 and 2,2-DMB. The filled symbols are for mixture permeation and the open symbols are for unary permeance. We note that the 2,2-DMB permeance in the mixture is reduced by about 2 to 3 orders of magnitude below the value for unary permeance, whereas for NC6 the permeance in the mixture is almost the same as the unary permeance. To understand this strong reduction in the component permeance for 2,2-DMB, we have to understand that the mixture adsorption is dictated by entropy considerations. 2,2-DMB is a branched alkane molecule that prefers to locate at the channel intersections, and there are only 4 channel intersections, and therefore if you look at the unary isotherm for 2,2-DMB, we will note that the unary isotherm is limited to a saturation capacity of 4 molecules per unit cell. Normal hexane can locate along the straight channels, can locate along the zigzag channels, and achieves a total saturation capacity of 8 molecules per unit cell. So in a mixture of 2,2-DMB and NC6, the mixture adsorption is shown by the fill symbols. The red ones are for normal hexane and the green squares are for 2,2-dimethylbutane. We note that with increasing pressure in the bulk gas mixture, the normal hexane loading increases at the expense of 2,2-dimethylbutane, and 2,2-dimethylbutane is virtually excluded from the pores due to entropy considerations. And the result is that the component permeance for 2,2-dimethylbutane is significantly lower than the unary permeance for 2,2-DMB. In a paper published in Journal of Catalysis in 1986, experimental data on adsorption of a ternary mixture of normal hexane, 3-methylpentane and 2,2-dimethylbutane are reported. And I plot this data in the following manner. The y-axis is the mole fraction of each of the components in the adsorbed phase as a function of the total mixture loading ranging from 0 to 8. Remember that the saturation capacity in MFI zeolite is 8 molecules per unit cell. And we note that as the mixture loading increases, in other words, as the adsorbed phase approaches saturation, the branched isomers are progressively excluded from the pore space at or to the benefit of the linear isomer. And we have direct experimental proof of entropic exclusion of the entropically challenged 3-methylpentane and 2,2-dimethylbutane that prefer to locate at the channel intersections, whereas normal hexane has no limitation with regard to its location. It can locate freely within the linear channels or the zigzag channels. It's also important to note that we had not been aware of this publication because the title of this paper does not suggest that it has anything to do with entropic separations, or it has anything to do with separations of normal hexane and 3-methylpentane or 2,2-dimethylbutane. Indeed, we discovered this paper when we had made a presentation to Chevron Corporation on the use of molecular simulations to understand mixture adsorption. And Don Santilli was one of the research scientists who was present in the room, and he stood up and told us about his paper that gave direct proof of entropic exclusion. And in our own paper, we compared the data from molecular simulations with Santilli's experiment and published these results in 2001. In a patent awarded to Universal Oil Products located in Des Plaines, Illinois, a set of pulse chromatographic experiments are reported for separation of hexane isomers. The volume fraction of the hexane isomers in the eluted sample is plotted against the volume of the eluent, and the sequence of elution is dibranched isomers, the monobranched isomers, 3-methylpentane, 2-methylpentane, and the last component to elute is the normal hexane. So the hierarchy of adsorption strengths is dibranched, monobranched, and linear isomers. The UOP patent does not specify the adsorbent precisely. It says the adsorbent may be silicolite, ferrite, zeolite beta, MAPO31, SAPO31, SAPO11, zeolite X, zeolite Y, etc., etc. We performed molecular simulations for a wide variety of zeolites in order to decide which component is capable, or which adsorbent is capable of producing these results for separation of hexane isomers. On the basis of screening a wide variety of adsorbents, we concluded that these pulse chromatographic experiments can only be produced by using MFI zeolite. I show here molecular simulations of adsorption of 5-component mixtures in MFI. The mole fraction in the adsorbed phase is plotted as a function of the total mixture loading varying from 0 to 8. 8 is the saturation capacity, And we note that as the mixture loading increases beyond a value of 4, recall that the monobranch and the dibranch isomers can only locate at the channel intersections, and therefore these are entropically challenged. And as the mixture loading is increased beyond 4, the composition of the adsorbed phase becomes increasingly in favor of the linear isomer, and the monobranch and the dibranch isomer are progressively excluded from the adsorbed phase. This is not a direct proof of that the simulation results provide an explanation for the UOP pulse chromatographic data, but in a conference, or in the International Conference on Chemical Reactor Engineering held in Hong Kong in 2002, Baron Smith and I presented a joint plenary lecture where we presented a comparison of the UOP pulse chromatographic experiments with our molecular simulation results in order to demonstrate the power of molecular simulations in choosing adsorbents for any specified separation. After our presentation, one of the scientists from UOP came to us and told us privately that our results were correct, and they indeed confirmed the UOP experimental data. We now demonstrate the principle of exploiting entropic effects to separate the isomers of hexane using mordanite as adsorbent. Mordanite has a structure that looks like this. We have a 12-ring channel, which is one-dimensional channel with these dimensions. Connected to these channels are side pockets, but these side pockets are small, and none of these pockets are able to adsorb the hexane isomers. The isomer adsorption occurs in the main 12-ring channel. Now, let's take the example of adsorption of normal hexane, 2-methylpentane, and 2,2-dimethylbutane. Hexane has a longer, normal hexane has a longer footprint, and within a certain length, from here to here, of mordanite adsorbent, we can locate a total of 1, 2, 3, 4, 5 normal hexane molecules at a certain temperature and pressure conditions in the bulk phase fluid surrounding the mordanite crystals. 2-methylpentane has a shorter footprint, and within the same length of mordanite adsorbent, we can accommodate 1, 2, 3, 4, 5, 6, 7 molecules of 2-methylpentane. If we proceed to the dibranched isomer 2,2-dimethylbutane, which has the still shorter footprint, we can accommodate 1, 2, 3, 4, 5, 6, 7, 8, 9 molecules of 2,2-dimethylbutane. The saturation capacities of these guests would be in these proportions shown here. And the differences in the saturation capacities can be judiciously exploited to separate the hexane isomers. When we talk about exploiting the differences in the molecular footprints of the hexane isomers in order to achieve separations, we need to realize that there are several conformations of each of these hexane isomers, and we have a distribution of footprints. In order to demonstrate that, let's have a look at the animations for normal hexane. We can see the variety of conformations the linear isomer can assume when adsorbing within the 12-ring main channels. The same thing is true for 2,2-dimethylbutane, that also has a number of conformations, and this produces a distribution of molecular footprints. By sampling several thousand conformations of each of the hexane isomers, it is possible to construct a probability distribution of the lengths of the footprints for normal hexane, 2-methylpentane, and 2,2-dimethylbutane. 2,2-dimethylbutane has the shortest footprint, say about 2.8 angstrom. 2-methylpentane has a footprint on average of 4.5 angstrom, and the normal hexane footprint on average is larger, which is about 5.5. Molecular simulations of the unary isotherms are shown here for normal hexane, 2-methylpentane, and 2,2-dimethylbutane, and you will note that at saturation, the loading of 2,2-dimethylbutane is higher than that of 2-methylpentane, and the loading of 2-methylpentane is higher than that of normal hexane. The saturation loadings are the inverse of the footprints of the corresponding isomers. To demonstrate the exploitation of differences in molecular footprints to separate hexane isomers, we performed molecular simulations for mixtures of normal hexane and 2,2-dimethylbutane. In the bulk fluid phase, the partial fugacities of each of the components is maintained equal to each other, and I plot the mole fraction of 2,2-DMB in the adsorbed phase as a function of the pore occupancy. The molecular simulation data are shown by the green squares, and we note that beyond a pore occupancy of 0.7, the mixture adsorption is in favor of 2,2-DMB, and at a pore occupancy of unity, in other words, at pore saturation, the mole fraction of 2,2-DMB in the adsorbed phase is 1. In other words, normal hexane is virtually excluded from the pores as we approach pore saturation. The continuous solid line are the IAST calculations using the unary isotherm data. So the entropic exclusion of the linear isomer is quantitatively predicted by the ideal adsorbed solution theory. It's important to note how important entropic exclusion principle is, because at post-saturation we have almost total exclusion of the linear isomer. For the industrially important separation of mixtures of normal butane and isobutane, we can exploit the differences in molecular configurations by using MFI zeolite. Within MFI, the isobutane molecules prefer to locate at the channel intersections because it has a freedom to also rotate at the intersections, and this freedom is lost if the isobutane molecules are forced to occupy channel locations. The normal butane molecule has no difficulty in aligning itself along the straight channels or along the zigzag channels. These are configurational bias Monte Carlo simulations from adsorption of normal butane isobutane mixtures. The mole fraction of normal butane is plotted against the pore occupancy, and as in the previous slides, we note that as the pore occupancy increases, the entropically challenged isobutane is increasingly excluded from the pores, and the mole fraction of normal butane approaches a value, say, around 0.9. For the industrially important separation of mixtures of normal butane and isobutane, we can exploit the differences in molecular configurations by using MFI zeolite. Within MFI, the isobutane molecules prefer to locate at the channel intersections because it has a freedom to also rotate at the intersections, and this freedom is lost if the isobutane molecules are forced to occupy channel locations. The normal butane molecule has no difficulty in aligning itself along the straight channels or along the zigzag channels. These are configurational bias Monte Carlo simulations from adsorption of normal butane isobutane mixtures. The mole fraction of normal butane is plotted against the pore occupancy, and as in the previous slides, we note that as the pore occupancy increases, the entropically challenged isobutane is increasingly excluded from the pores, and the mole fraction of normal butane approaches a value, say, around 0.9. Benzene and cyclohexane also prefer to locate at the channel intersections because there is an additional rotational degree of freedom, as shown in these MD simulations for benzene on the left and cyclohexane on the right. The preferential location of these molecules at the channel intersections have a profound influence on mixture adsorption. Here I show configurational bias Monte Carlo simulations for adsorption of ethene and benzene, red circles, propene and benzene, green squares. Benzene is much more strongly adsorbed than the alkenes, but as post-saturation is approached, the selectivity reverses in favor of the alkenes in both cases. Such selectivity reversals are important in the design of reactors for ethylation of benzene to produce ethyl benzene. That is important in the petrochemical industry. And further details are available in these publications. Let us change topics and move on to the separation of mixtures of 1-alcohols in the liquid phase. Remy and Denaye report a set of breakthrough experiments carried out in the liquid phase using SAPO34 zeolite as adsorbent. SAPO34 has the same structural topology as a Chabasite zeolite. It consists of cages of 316 cubic angstrom separated by 8-ring windows which have dimensions of 3.8 angstrom in this direction and 4.2 angstrom in this direction. Let's look at 3 of the experiments reported by Remy. We have mixtures of ethanol and propanol feed mixtures in equimolar proportions, and the breakthroughs show that the component to break through first is the longer alcohol 1-propanol, and the shorter alcohol ethanol is the second component to break through. Here is a breakthrough experiment for equimolar mixtures of ethanol and hexanol. The first component to break through is the longer 1-hexanol, and the last component to break through is the shorter ethanol. Here's the breakthrough experiment for methanol, propanol, and butanol. The first component to break through is the heaviest component, butanol. This is followed by propanol, and the last one to break through is the shortest methanol molecule. So these experiments are rather extraordinary because they show preferential adsorption of the shorter alcohol for liquid phase mixtures. Now, to understand these experiments, we carried out configurational bias Monte Carlo simulations for various mixtures in Chabasite zeolite. We begin by analyzing the separation of mixtures of ethanol and 1-propanol. The unary isotopes of ethanol are shown here. This is for 1-propanol. The ratio of the Henry constants for 1-propanol is 200 times higher than the Henry constant for ethanol. However, the saturation capacity of ethanol is a factor 2 higher than the saturation capacity of 1-propanol. With ethanol, you can put or locate 4 ethanol molecules in 1 cage. With 1-propanol, only 2 molecules per cage can be accommodated. We now examine mixture adsorption in Chabasite of ethanol 1-propanol. We performed molecular simulations for adsorption of mixtures of ethanol 1-propanol. In the bulk phase, the partial fugacities of both components are maintained equal to each other. And in this graph, the simulation data are plotted. The adsorbed phase mole fraction of ethanol on the y-axis and the total occupancy within the pores on the x-axis. 1-propanol, being a longer alcohol, is much more strongly adsorbed. The Henry constant for 1-propanol is 200 times higher than that of ethanol. And at low pore occupancy, say below 0.5, the mixture adsorption is strongly in favor of 1-propanol. However, as the pore occupancies increase beyond about 0.7, the mixture adsorption reverses in favor of the shorter ethanol molecule, because the ethanol molecule has a higher saturation capacity and is therefore entropically preferred, whereas 1-propanol, being a longer molecule, has a lower packing efficiency and is entropically challenged. The solid blue line are our IAST calculations using input data obtained from the unary isotherms. And it is important to note that the selectivity reversal is anticipated almost quantitatively by the IAST. We rationalize the CBMC mixture adsorption data by a simple checkerboard representation of Chabasite zeolite. A single cage of Chabasite zeolite can be considered to have 4 adsorption sites that can be occupied by 4 ethanol molecules. Alternatively, a single cage of Chabasite zeolite can be accommodated by 2 1-propanol molecules. At low pore occupancies, the component loadings are dictated by binding strengths. The situation is different at high pore occupancies. Let's consider a cage with 4 adsorption sites here. There's 1 adsorption site free, and that can only be occupied by ethanol and not by 1-propanol. Let's consider another cage of Chabasite zeolite here. There is 1 propanol occupying 2 adsorption sites, and 2 adsorption sites are free. There are 2 alternatives. These sites can be filled by 2 ethanol molecules or 1 propanol molecule. Let's consider another cage of Chabasite zeolite represented here. It has 1 propanol molecule and 1 ethanol molecule occupying 3 sites. There's 1 site available. This can only be occupied by ethanol. So the message that emerges from this simple representation here is that it is easier to fill vacant sites by ethanol at high pore occupancies. Because 1-propanol requires 2 adjacent sites to be vacant, whereas ethanol does not have that constraint. So pore occupancy is an important factor in mixture adsorption in the liquid phase. Let us quantify the adsorption of mixtures of ethanol on 1-propanol on the checkerboard by using the Boltzmann expression for the entropy. S is KLNW, that is also engraved on his tombstone in Vienna. K is the Boltzmann constant, and for a binary mixture of a Kamer, green, and an Elmer, marked blue, the expression for W, Wahrscheinlichkeit, is simply written in terms of the number of Kamers. NL is the number of Elmers, and M represents the total number of adsorption sites on the checkerboard. For the special case of ethanol 1-propanol, K is 1 and L is 2, which is 1-propanol. The factorials can be determined using the Stirling approximation. This is the expression of the Stirling approximation to determine the factorials, and S is K, L, and W can be determined for the ethanol 1-propanol mixture. Using the concept of entropy maximization, we can determine the adsorbed phase mole fraction of ethanol as a function of occupancy on the checkerboard, and the expression for maximum entropy is shown by the continuous black line here. At low pore occupancies, there is no entropic preference for either ethanol or 1-propanol. However, as the pore occupancy theta increases, entropy considerations favor the smaller ethanol molecule because there are more ways in which the Kamer, which is ethanol, can be arranged on the checkerboard. Also important to note, at the pore occupancy of unity, the adsorbed phase mole fraction for entropy maximization is unity. In other words, from considerations of entropy alone, maximum entropy is achieved by filling the checkerboard with the smaller ethanol molecules. In practice, we have to use the expression G equals H minus Ts, and the equilibrium is between the bulk gas mixture and the adsorbed phase mixture is dictated by the minimum in the Gibbs free energy, which combines the enthalpic contribution and the entropic contribution. The entropic contribution is already shown by this black line, and if we combine the entropic and the enthalpic contribution and determine the minimum in the Gibbs free energy, we obtain the blue line that coincides almost quantitatively with the IAST calculation. So the minimum in the Gibbs free energy yields the blue line, and beyond a certain pore occupancies of say 0.7, the mixture adsorption equilibrium is driven by entropy effects that favor the shorter alcohol. And at a pore occupancy of unity, the adsorbed phase mole fraction consists entirely of ethanol. So by combining the Boltzmann concept of S is KLNW with the minimization of free energy, we can explain in a very simple way the selectivity reversal in favor of ethanol that manifests at high pore occupancies. Precisely analogous explanation holds for mixtures of ethanol and 1-hexanol. The unary isotherms for 1-hexanol are shown here. This is for unary isotherm for ethanol. The saturation capacity of ethanol is 4 times higher than the saturation capacity of 1-hexanol. Only one molecule of 1-hexanol can be located within a single kg of Chabasite zeolite. So the ratio of saturation capacities is 4, but the binding strength of 1-hexanol is 30,000 times higher than the binding strength of ethanol. On plot here, the adsorbed phase mole fraction of ethanol as a function of total occupancy. These are the molecular simulations for the adsorbed phase mole fraction. And we note that below a pore occupancy of about 0.4, the selectivity is in favor of the longer 1-hexanol molecule due to its stronger binding with the framework. However, entropic considerations favor the shorter ethanol molecule because there are more ways to arrange ethanol molecules on a checkerboard representing the adsorption sites within Chabasite zeolite. At pore occupancies higher than about 0.5, the selectivity reverses in favor of ethanol, and at occupancies approaching unity, the adsorbed phase mole fraction is almost pure ethanol. Zeolites such as Chabasite, DDR, 4A zeolites are used for separating water-ethanol mixtures by evaporation. Let's consider mixture adsorption of water ethanol in Chabasite. Here are the unary isotherms for water, red circles, ethanol, green squares. We note that the saturation capacity of water is 16 molecules per kg approximately, and for ethanol it's 4 molecules per kg. At low pore occupancies, the mixture adsorption is in favor of ethanol that has the higher binding strength. However, for pore occupancies larger than about 0.8, the selectivity reverses in favor of water because the vacant adsorption sites within a cage are more easily filled with the smaller water molecules, and ethanol is entropically challenged in comparison with water. So entropy effects are of vital importance in the modeling and design of membrane evaporation units. It's also important to note that the selectivity reversal in favor of water is anticipated by the ideal adsorbed solution theory. The entropy effects that manifest during separation of linear alcohols in Chabasite also hold for separation of linear alkanes. Here are configurational bias Monte Carlo simulations for linear alkanes in Chabasite. The saturation capacity of methane is 6 molecules per kg. Here's the computational snapshot showing 6 per kg. The saturation capacity for ethane is 5 per kg. 5 per kg. The saturation capacity of propane is 4 per kg. Butane is 2 per kg. Pentane is also 2 per kg. Hexane, heptane, and octane are all 1 per kg. Therefore, you could exploit differences in cage capacities to effect separations of mixtures of linear alkanes that favor the shorter alkane at pore saturation. To demonstrate this, we carried out configurational bias Monte Carlo simulations for various mixtures: methane, ethane, ethane, propane, normal butane, normal hexane, propane, hexane, pentane, hexane. The adsorbed phase mole fraction of the shorter alkane is plotted against the total mixture occupancy. For all these mixtures, the adsorption selectivity favors the shorter alkane when the pore occupancy is larger than about 0.6. The explanation of these entropy effects is precisely analogous to that highlighted earlier for separation of 1-alcohol mixtures. The computational snapshots of the linear alkanes NC9, NC10, and NC25 in LTA5A zeolite are shown in these pictures. LTA5A zeolite consists of cages of 11 angstrom diameter separated from adjacent cages by 4.3 angstrom windows. Within a single cage, 2 of NC9 molecules can be accommodated, or 2 NC10 molecules, but for NC25, 1 molecule occupies 2 adjacent cages. Therefore, for mixtures of, say, NC10 and NC25, at pore occupancies close to saturation, entropy effects will favor the shorter NC10 molecule rather than the most strongly adsorbed NC25. Here is a picture of the aromatics complex in the petrochemicals industry. We have the catalytic reformer for increasing the aromatics content using naphtha as feedstock. We have a reformate splitter with C8 and C9 aromatics. These are sent to a xylene splitter where the C8 aromatics are removed from the top and C9 aromatics are removed from the bottom. The C8 aromatics are sent to a simulated moving bed adsorber. In current industrial practice, we use barium X zeolite. There are two products from the SMB adsorber. The raffinate contains orthoxylene, metaxylene, and ethylbenzene, and the desired extract contains paraxylene. If you follow the tops from the reformate splitter, we have benzene, toluene, and non-aromatics. The aromatics, especially benzene and toluene, are recovered from this mixture by using extractive distillation. The benzene is sent to a alkylation unit to produce ethylbenzene. Remember a few slides ago we were talking about ethylation of benzene using MFI zeolite and how important entropy effects are in deciding the catalytic performance. The ethylbenzene is sent to a dehydrogenation reactor to produce styrene. The separation of the desired styrene from ethylbenzene occurs in a vacuum distillation unit, and there is potential for replacing this vacuum distillation column by an adsorption unit using a suitable MOF. So in the subsequent slides, we will consider adsorbents for separation of C8 aromatics and for styrene ethyl benzene separations. A very good description of the separation of xylene isomers using barium X zeolite is available in the thesis of Costa that is available online. And I use the information and the figures from this thesis to illustrate a few points regarding entropy effects. Let's consider first the adsorption of metaxylene in barium X. Within a single alpha cage, the location of the first two molecules of metaxylene is relatively easy. But the location of a third molecule within the alpha cage is energy demanding because it requires a reorientation of the meta isomer. The same is true for the ortho isomer. In contrast to metaxylene, the placement of the third molecule of paraxylene within BAX is not energy demanding because the longer paraxylene molecule can be located in the plane of the window and is stabilized by interactions with the oxygen atoms of the framework. There is no corresponding adsorption of metaxylene or orthoxylene at the window sites possible. So, summarizing, the difference in the adsorption of meta-isomer and orthoisomer with the para-isomer is that with the para-isomer, the loading of 3 molecules per kg is more easily achieved than with the ortho and the meta-isomer, for which the location of the third molecule per kg is an energy demanding task. The thesis of Costa contains an interesting and important graph showing the selectivity of paraxylene with respect to metaxylene as a function of the total loading per alpha kg of faugisite zeolites. Blue represents barium X and the red symbols represent sodium X. For both these cation exchanged zeolites, the px to mx selectivity is the same up to a loading of 2 molecules per alpha kg. For barium X zeolite, the selectivity increases in favor of the para-isomer as the loading is increased beyond 2. This is because the placement of the third molecule of metaxylene is an energy demanding task, whereas the placement of the third molecule per alpha kg of paraxylene is relatively easy because the third molecule can be located in the plane of the windows. So the selectivity in favor of paraxylene is due to entropy effects. Let us summarize the story that has emerged so far. Under post-saturation conditions, mixture adsorption favors the guest component that has a higher saturation capacity. If the feed mixture is in the liquid phase, post-saturation conditions are assured. In order to achieve high saturation capacities of the component we wish to selectively adsorb, we should choose materials that allow optimal packing of the guest component. The optimal packing could be, for example, face-to-face packing of crisps in a cylindrical container of Pringles or face-to-face packing of pieces of chocolate, triangular in shape, in a Toblerone container. Within the triangular channels of Fe2BDP3, the stacking of 1,3,5-trichlorobenzene occurs in a face-to-face manner. This results in a very short footprint as compared to the footprints of 1,2,3-trichlorobenzene and 1,2,4-trichlorobenzene that cannot stack vertically. Therefore, these Toblerone-shaped channels structures may be employed to selectively adsorb 1,3,5 isomer from a mixture with 1,2,3 and 1,2,4 TCBs. Consider the separation of xylene isomers using AFI zeolite. AFI zeolite consists of one-dimensional channels. The shortest channel distance is 7.3 angstrom, and in the grooves, the distance of separation is 8.4 angstrom. Orthoxylene has a size that fits nicely within the grooves, and the packing of the molecules is face-to-face and within the same channel length, a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10.5 orthoxylene molecules can be located. The other isomers, metaxylene and paraxylene, cannot be located in the grooves and have a much longer footprint, and the number of molecules that can be located within the same channel length is considerably smaller. For example, here we have half, 1.5, 2.5, 3.5, 4.5, 5.5, 6.5 of metaxylene, 1, 2, 3, 4, 5, 6 of paraxylene. The unary isotherms determined experimentally for orthoxylene confirm that the higher saturation capacity of orthoxylene is due to face-to-face packing of orthoxylene within the tubes. Indeed, experimental data on transient breakthroughs of xylene isomers shows that orthoxylene is the most strongly adsorbed component and breaks through last. However, in industrial practice, we need an adsorbent that is selective to paraxylene and not orthoxylene. Within the 8.5 angstrom sized lozenge shaped channels of MIL47, we achieve a commensurate stacking of orthoxylene. If we look into the channels, we see face-to-face stacking of orthoxylene. If we look at the stacking from below, we see that the length of the orthoxylene molecules is commensurate with the shape of the channels. You see snugly fitting your channels. If we look at the stacking of molecules in this direction, we see two rows. This is the front row and the back row. So the molecules in the front row are the alternate molecules, and this is the back row. So we have commensurate stacking of orthoxylene viewed in three different ways. And for mixture adsorption, the experiments of Finzi show indeed that mixture adsorption is orthoselective. Our search for a para-selective adsorbent continues, and MIL47 is not yet the solution. Even though MIL47 is not a suitable candidate adsorbent for xylene separation, it is suitable for separating styrene from ethyl benzene as an alternative to the vacuum distillation columns being currently used in industry. The difference between styrene and ethyl benzene is that styrene is a flat molecule, and within the 8.5 angstrom lozenge-shaped channels of MIL47, we have a commensurate face-to-face stacking of styrene molecules, whereas ethyl benzene, the side chain, the ethyl chain, is not in the same plane as the benzene, and the stacking of ethyl benzene within the channels is less efficient. The net result is that mixture adsorption is in favor of styrene. This has also been confirmed experimentally in breakthrough experiments. The slide shows molecular simulation data to demonstrate styrene-ethyl benzene separations using MIL47. These are the unary isotherms. We note that the styrene has a higher saturation capacity, and for mixture adsorption, entropy effects favor the adsorption of styrene because of commensurate stacking within the lozenge-shaped channels. For optimal stacking of para-xylene within an adsorbent, we need channel dimensions which are about 10 angstrom, so that para-xylenes can stack vertically. One such candidate is the MOF MAF-X8 that has 10 angstrom channels, and the computational snapshots show that the para-xylene molecules can stack face to face in a vertical manner, and this is also evident in this movie animation. Optimum stacking of para-xylene can be achieved in the one-dimensional zigzag channels of cobalt CuK1, as reported in this paper by Yoon and co-workers. These are the unary isotherm data that clearly shows a higher saturation capacity for para-xylene than with other C8 hydrocarbons. However, the selective adsorption of para-xylene from mixtures has not been established experimentally, either from mixture adsorption experiments or from breakthrough experiments. And this is a subject for future MOF development and work. The takeaways from this presentation are summarized in the slide. Entropic separations manifest near pore saturation. Entropic separations rely on differences in saturation capacities and packing efficiencies. The saturation capacities depend on molecular configurations, molecular footprints, molecular sizes, etc. It's important to note that the entropy effects are anticipated by the ideal adsorbed solution theory. And one important characteristic of entropic separations is that we have near total exclusion of entropically challenged component at pore saturation. And in this presentation, we have used the simple Boltzmann expression, S is equal to KL and W, in order to explain and elucidate entropy effects using a checkerboard analog of adsorption sites within the pore topology. Benzene and cyclohexane also prefer to locate at the channel intersections because there is an additional rotational degree of freedom, as shown in these MD simulations for benzene on the left and cyclohexane on the right. The preferential location of these molecules at the channel intersections have a profound influence on mixture adsorption. We begin our discussions by considering the separation of hexane isomers, normal hexane, NC6, and 2-methylpentane using MFI zeolite. MFI stands for mobile 5, consists of a set of intersecting channels. This is one unit cell, and one unit cell has 4 intersection sites shown here. These are the intersection points. These are the zigzag channels. These are the straight channels, and the channel dimensions are 5.5 angstrom. These are the unary isotherms, where we see that the component loadings of both normal hexane and 2-methylpentane are identical in the Henry regime, but the saturation capacities are different. Normal hexane has a saturation capacity of 8 molecules per unit cell, whereas the saturation capacity of 2-methylpentane is restricted to about 4 molecules per unit cell. And the reasons are shown by the computational snapshots here, where normal hexane, the linear isomer, can locate anywhere along the straight channels or along the zigzag channels. However, 2-methylpentane, due to configuration and consideration, requires more legroom and prefers to locate at the intersection sites. And there are only 4 intersection sites per unit cell, and therefore the saturation capacity at say a pressure of 10 to the 4 pascals is about 4 molecules per unit cell. Only if you go to a very high pressure, say 1 megapascal, you can manage to locate 2-methylpentane within the channels. Let's first look at the unary isotherms of methanol, ethanol, 1-propanol, 1-butanol, 1-pentanol, and 1-hexanol in Chabasite zeolite. These unary isotherms were determined from configurational bias Monte Carlo simulations. The loadings expressed in molecules per kg of Chabasite are plotted against the fugacity in the bulk fluid phase. We note that the saturation capacities decrease with increasing chain lengths, going from methanol to 1-hexanol. The saturation capacity changes from about 6 molecules per kg to 1 molecule per kg, and these are highlighted here by computational snapshots. This shows methanol, and you can locate 6 methanol molecules within 1 kg of Chabasite. You can only locate 4 molecules per kg of ethanol, 2 molecules per kg of 1-propanol, 2 molecules per kg of 1-butanol, 1 molecule per kg of 1-pentanol, 1 molecule per kg of 1-hexanol. With increasing chain length, the binding strength of these 1-alcohol increases. In other words, the binding strength of ethanol is greater than the binding strength of methanol, and that is reflected in the fact that with increasing chain length, the isotherms move to the left. So the Henry constant increases with increasing chain length, but the saturation capacity decreases with increasing chain length. Let us see how that plays out. Based on the results that have been presented in the previous slides, we can devise a improved alkane isomerization process. Here we have a feed mixture that is sent to an isomerization reactor that uses mordanite as catalyst. The reactor increases the proportion of branched isomers by isomerizing the normal and monobranched isomers to the desired dibranched isomers. The reactor product is sent to a separation unit that uses MFI as an adsorbent. 2 streams are recovered from the adsorption separation section. The stream containing normal hexane and the monobranched isomers 2-methylpentane and 3-methylpentane are recycled back to the reactor for further isomerization to the dibranched isomers, and the dibranched isomers from the adsorption separation unit are recovered and sent to the gasoline pool for producing high octane gasoline.